Unit 3, Video Lecture 1, Historical Development of the Atom. Why does matter behave the way that it does? Can we predict how matter will behave? What do we need to know in order to predict its behavior? And what is the structure of matter? The answers to these questions have been looked for over the past 2,000 years. Many people contributed to the concept of the atom. They came from various countries and contributed their various expertise to the major problem of the day. What does matter look like? From this struggle came an entirely new theory of an atom and a new type of physics, quantum physics. Democritus was the first person to suggest answers to our questions. Democritus was a Greek philosopher that lived between 460 and 370 BC. And his main question that he pondered was the question of division. If you take a chunk of gold and divide it into two, what do you end up with? You end up with two smaller pieces of gold. And you divide one of those two smaller chunks into two, what do you end up with? Two even smaller chunks. Can you keep that up forever? Democritus says no. He says at some point there must be an indivisible particle of matter. He called it the atom. He actually called it atomos, but we translate that to atom. Democritus concluded that all matter is made up of atoms, that these atoms are indivisible. He also said that all atoms are the same, and it's the arrangement of them that determines the type of substance that's formed. A slightly more famous Greek disagreed, saying that matter was made up of four elements: fire, water, air, and earth. Aristotle said it was the combination of those four elements that caused different things to be made. For example, clouds would be made of water and air. Wood, on the other hand, would be made up of all four of the elements. So over the next years, a lot of experimental work was done. However, modern chemistry didn't start until the 1700s. John Dalton was the first modern scientist to suggest an atomic theory. Dalton experimented with gases and used Democritus's idea that all substances were made of atoms, not fire and water, air and earth, like Aristotle suggested. Dalton also believed that atoms are small and cannot be created, divided, or destroyed. Dalton was the first one to suggest a modern atomic theory, and in it, he said that all matter is made of atoms, which is indivisible and indestructible. That atoms of the same element are the same, which is why they're elements. And that atoms of different elements are different. That's how we tell apart the different elements. And that atoms join together to form other substances. These compounds join together in whole number ratios. So like water, H2O would have that 2-to-1 hydrogen to oxygen ratio. Dalton also said that the rearrangement of atoms is a chemical reaction. Dalton's atomic theory held true until the late 1800s, early 1900s, when J.J. Thomson used what's called a cathode ray tube, which made use of positive and negatively charged plates, and removed gases from this and showed that the particles inside atoms were attracted to a positive pole. Thomson's cathode ray tube experiment showed that when we took a sealed tube with gas at low pressure and ran electricity through it, we would get this glowing beam that existed. When magnets were placed near the tube, we would see that the glowing beam would bend away from the negative to the positive plate. The negative electrons were attracted to the positive part of the magnet.
To demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream. Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
Thomson's model of the atom provides the first evidence that atoms are made up of smaller particles. It provided definite proof of the existence of the electron and the nature of the proton. Thomson's model of the atom is called the plum pudding or the chocolate chip model of the atom. In it, we have these negatively charged electrons that exist on the mass of positive charge. So if we think of this as a cookie, the negative electrons would be examples of the chocolate chips, and the cookie dough would be the positive mass. Over the next 50 years, there's the development of new technology, the discovery of radioactive particles, alpha particles. And with this development of new technology, we can get new scientific data. Ernest Rutherford fired alpha particles at gold foil. And behind the gold foil was a screen coated with zinc sulfide, and which glowed when it was struck by particles. One of the things that we can see is that more particles were deflected than what Rutherford originally thought. Originally, he expected these particles, for the most part, to go through. However, what happened was we saw some great differences. We saw some great differences in the angles at which the alpha particles hit. Some bounced back like they hit something solid.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
In the following pictures, there's a target hid by a cloud. To figure out what the shape of the target is, we shot some beams into the cloud and recorded where the beams came out. Can you figure out the shape of the target? Here's the first one. And the second. Target 1 was a triangle. These flat shapes, the flat sides of the triangle, caused those particles to be bounced off at right angles to how they came. Target 2 is a circle. Based on where it hit, some particles, like 3, were bounced straight backwards. Some particles, like 1 and 5, bounced straight through, and others were deflected upwards and downwards, like 2 and 4. Rutherford found that most of the particles passed right through, and that very few were deflected. Very few were greatly deflected. Rutherford was said to have called it the attuned to howitzer shells bouncing off tissue paper. This led him to believe that the atom, or that the nucleus, is very, very small, that it's very, very dense and is positively charged. So we see that the majority of the particles went through the foil, so the majority of the atom was empty space. A few were deflected backwards, indicated they hit a solid object. He concluded that the atom has a solid core or nucleus, and this nucleus had a positive charge. The nucleus must be the densest part to cause that great bounce back. Therefore, the majority of an atom's mass must be in the nucleus. The negatively charged particles, or the electrons, orbited outside the nucleus. So here we see the electrons on the outside of Rutherford's atom. We see the electrons on the outside of Rutherford's atom. And we see that dense center nucleus in the middle. There's our electrons on the outside. James Chadwick provided for the existence of a neutron. What he did is he found out that the atomic mass was not equal to the atomic number of an element. There had to be a third particle that existed that had mass. And this third neutral particle was called the neutron. With the advent of new technology, we came up with new or modern atomic theories. One of the first ones was Niels Bohr. Bohr showed that atoms' electrons are capable of absorbing and emitting energy, but only in specific amounts. Unlike Rutherford's model of the atom, Bohr's model had these electrons orbiting the nucleus like planets around a sun. But they stayed in energy levels. That's what those N's are. And different levels of the atom were different energy levels. Now, electrons weren't set. They didn't have to stay in that one energy level. An electron could jump from energy level 2 to energy level 3 if it brought energy in. If the electron came from energy level 3 and dropped back down into energy level 2, it would release energy. This is that change in energy here. And then finally, modern atomic theory. Modern atomic theory makes use of those energy levels like Bohr's model has, but instead of having those electrons orbit around in a fixed position, these orbitals, this region of space around the nucleus where an electron is most likely to be found, says that this electron, while it's traveling in here, can travel anywhere within this particular energy level. An orbital can hold a maximum of 2 electrons. This atomic orbital and energy level, this quantum theory, led to that new discovery, that new field of physics, quantum physics, and will be discussed in greater detail a little bit later.